Hello and welcome back to the lab. Today on the bench is, again, the FG506. This is the third installment on this particular unit, and probably will be the last one, unless there's some additional questions, because we have to get this back to its owner. After the first video, I was in communication with Dennis, who is the engineer that designed this particular instrument. And in discussing with him some of the features and functions, we had some great conversation, and I very much enjoyed getting to talk about some pretty cool stuff that maybe should have made it, but never quite made it to market. So, at Dennis's request, in the description of this video is going to be a link to his website. So he's written a couple of books on different units and a few other things. So head on over there and check out the content if you would like some additional information. The reason for the third video is this unit hasn't shown off as much as well as we'd like it to. Partly the reason for that was, well, it's kind of hard to show off the functionality of a unit that didn't work. No fault of the engineering. The engineering was solid. Time just wasn't kind. As a restorer, the problem is if you're going to do a unit like this, especially one of these where only 6 were made, only 2 are known to exist, and it's of historical significance, the question there is always, how far do you take it? And that was really something that I may have been a bit cautious of in the beginning, and we'll get into some of that. But this unit's current owner did want it to work before it's destined to go to its final resting place. He wants to use it on his bench before it gets moved on. It's not staying here. The main goal of this was to bring it back to functionality, and I did that in kind of a stair-step fashion. If I'm presented with a TM500 plug-in of not historical significance, for example, a multimeter that thousands were made, I have kind of a standard process of what to look for, what to check, what to go into, and how to restore one of these units. The switches almost always need to be cleaned. I have not come, a unit has not come into the lab, that, at least for my personal use, that didn't need some TLC on the mechanics and the electromechanical controls. It also has some TM500 sockets, or not TM500, some TI sockets that are known sore spots, which unfortunately this FG506 had as well. And that was kind of where I was a bit too cautious, was where if it was a unit that was not historically significant, would have gone ham, just replaced the sockets, did everything that I know I should do. But I tried to get this one working with the least amount of interference to keep it as original as possible, especially with it being a one of 2 that are only known to exist. Unit 4 and Unit 6 are the only ones that we know are still around. Unfortunately, we did not restore, or we did not film any of the restoration due to the fact that this unit deserved my full focus and attention, especially with some of what we had to do. So, in the previous video, we addressed the socket that was on this op amp up here, but there was 2 more, one here and one here. And when I was doing the demonstrations in the previous videos, the oscillator kept dying when it wasn't supposed to. So as you set these 2 switches, which we'll demonstrate a little bit later, the oscillator's not supposed to stall, and that's what was happening, was it was stalling. And that was because of the TI sockets. So I had to replace this TI socket here. We'll zoom in. So we had to replace this TI socket right here, but as you'll notice, this pin's flown out and connected. That pin's flown out and connected. There's a whole bunch of stuff on the back side of this socket that had to get up correctly. There's a lot of rework, at least on this one, redesign that happened right around this socket. This socket up here, right there, was much more straightforward in getting it replaced. It was just pop the socket out, pop the new one in. But also we have a I believe it's an 18-pin chip on a 16-pin socket. And so there's a lot of wild stuff going on around here. And I'll flip it over and I'll show you what we had to do. I had to completely rework this section of the board, and this is what made me really, really nervous. There's a lot of jumpering going on. All the traces that go into this socket have been cut, rerouted. This capacitor has been added. This capacitor was added. This resistor runs off to this trace. Now, I did not like the way it was originally done because it was laid and then the wires snaked out of these two pins to come up here, and there was less than a millimeter of clearance between the pins and the insulation of the wire. So this leg got a little extended. Not a big deal when I was doing that rework, but I had to rework this entire section. And especially on a unit like this, that's a 1 of 2, you've got one shot. Like, I had to be extremely careful getting all of this stuff hooked back up, taking it all apart, not lifting any pads. As you can see, like, here's a trace that's been cut and reworked right here. And there's our 2 extra pins. So it's a 16-pin socket on an 18-pin hole, or on an 18-pin footprint. And just making sure there were no bridges, no nothing. This was extremely nerve-wracking to get that reworked and reworked appropriately. Because if anything went south, there's no replacements. I mean, if the PCB, something happened to the PCB, something shorted out, blew up, like, there's not a lot of stuff I could have done to recover from an oops. So lots of documentation, very meticulous, and lots of photos, making sure all this stuff got in and got put back together correctly so the unit worked. We made a comment on the first video about this. This was a design change. This wasn't hand-selected parts. So this would have been a design change. Something would have needed to be adjusted to get the unit functioning. So that's why some of the parts are stood off the board like that. These would have been added in future PCB designs and future PCB revisions. If the unit had gone into production, they would not have stayed that way. One of the other things that I got incorrect was up here. So we had this flying lead up here, which was connecting these components, which was also paralleled by a PCB trace. Originally, I thought this would have been a ground. Somebody needed a better ground reference than the PCB was giving them. And it turns out it's not ground. It's actually part of the VCO. So given that the VCO has a 0 to 15 volt full scale, 1 hertz essentially, all the way up to 100 kilohertz, we only have 15 volts. When that divides down, at the lowest ranges, the VCO is sensitive to microvolts. We only have 15 microvolts that we're playing with. So this needed to be additional conductance path for current for the VCO, because when we're talking about a 15 microvolt signal, the resistance on the PCB trace alone, the loading was a little too much, and it was messing with the accuracy of the VCO. So this is part of the VCO circuit, and it's a conductance path for essentially microvolts. Socket-wise, so we had a TI socket here, we had a TI socket there and there. These sockets are incredibly high-quality sockets, including these. So I only had to do those 3. Unfortunately, well, for my nerves at least, that's one of the most critical sockets, and it also had a lot of the rework. So it just took some time. One step at a time, work through it, and it'll get done. But that's why we didn't turn the camera on, because I needed full focus to make sure nothing happened. So while I was prepping to demonstrate this, I made a mistake. I made several. We have a 10, 100, and 1000X modifiers. 1X is all the switches out. So from this would be the configuration for lowest frequency to highest frequency. This knob's all the way up. The 1000X multiplier is pushed in, sine wave, highest amplitude. Now it's going to sweep the 4 decades. When I had the 10X, it was only sweeping 3 decades. So that was, so this is now the correct configuration for a 3-decade sweep, which we'll show on the scope here in a minute. Okay, distortion. This unit was plagued by some distortion issues, and it was not performing near as well as it should. It was running about, well, depending on what was going on, I saw it as high as 9% THD, and it's supposed to be 0.5 or below. We have 3 controls that primarily control that. We have the lower side of the waveform, upper side of the waveform, and the symmetry control. And it was a balance of all 3 of these controls to get the sine wave shaper to take it from a triangle wave output to a sine wave output. Now that's done with diodes and breakpoints in this one, in this particular unit. So the amplitudes and things were absolutely critical to get that working right, and that is a very, very fiddly adjustment to get that as good as I can, and I got it down to 5.2. Slightly high, but very usable, which we'll show right now. Okay, here we are at a stable-ish about 1 kilohertz, and our sine wave looks a lot better than it did before. It was pinched in, and it was more triangle wave at the top instead of rounded, so we did have an amplitude problem. Now, this is a function that this oscillator is supposed to do, depending on how you have the front 2 knobs and the multipliers set. You can actually freeze the waveform, and I can edit or adjust the frequency, and the unit's behaving exactly like it's supposed to, and the oscillator's not stalling anymore because the signals are going where they're supposed to go. Okay, distortion is 0.6 and coming down. The distortion meter is not warmed up yet, so it should stable out around 5.5, 5.4. I also think I'm going to warm up my spectrum analyzer because it might be cool to look at the distortion components of the sine wave shaper, but we'll have to let that wait and warm up. So looking at the input monitor from the distortion analyzer, we have a very solid sine wave and 1 kilohertz. This is actually externally referenced to nothing at the moment because my rubidium's not on. Whoops. Nope, I forgot. This is GPSDO. So the GPSDO is feeding this frequency counter right now, so I don't need the rubidium on. But if we watch the scope, we will kick it to 1x. Now we have a 1x frequency, which we expect. Actually, I'm going to move this so the notch filter in the distortion analyzer is not going nuts. Okay. Now, what we're going to do is gonna push the top button in, and now we have the frequency on the high side. So we'll give the frequency counter a second to catch up. So frequency counter, 101.7 kilohertz. So we're sweeping from an incredibly low frequency up to 101 kilohertz. Now when I push the bottom button in, it's going to start sweeping. And we're going to turn on the sweep blanking, so when it sweeps down, we won't see it. Okay, after a bit more switch cleaning, which I needed to do, we have 100 kilohertz. Actually, just so you guys can see the 5 microseconds per division, we have 100 kilohertz, so say at the frequency counter. And if I finally hit this bottom button the way it's supposed to be, we will see a 4-decade sweep, logarithmic sweep of frequency sweeping up and then sweeping down. Now if I hit the sweep blank, what will happen is the output will go to 0 while it's down sweeping. So if I hit sweep blank and we wait a minute, what we'll see, there it goes. Now we're sweeping up. When you see the trace fly around like that, that's just a because of the time base that I have set on the scope, the way it's triggering, it's acting a little, well, it's just an artifact of the trigger. Actually, what's interesting is on this scope, with the way it works, is we see the sweep up as a increasing amount of frequency. If I'll hook this up to the Riggle, and we'll actually see it come in from both sides as opposed to when it sweeps up and down in frequency. So we get the Riggle fired up, and we'll take a look at that. And here we are on the Riggle. Sweep should start here in a moment. And there it goes. And as we see, when it sweeps up in frequency, we see the frequency come in from both sides, just the way the scope displays and actually how the trigger functions. The trigger functions in the Riggle very differently than it functions on the Tech. So the way we're looking at this is a triggering artifact as opposed to a fault. If I turn off the sweep blank, we will actually see it sweep up and then sweep down. But it didn't look like this on the Tech scope because it would have swept from the edge over here. The trigger on the Riggle is in the center as opposed to being on the edge. So that's why we're seeing the sweep up and sweep down on both sides of the center line. Quick tweak of the symmetry control. Because this is an analog device, anytime you clean the switches, it could throw some things off. Cleaning the frequency switches messed with the symmetry, so I did need to tweak the symmetry control. But with cleaning the switches, I was at 0.52, now I'm at 0.22. So we're actually under spec, and we have a very, very nice sine wave coming out of this. And that's with no filters on the AA501 and everything warmed up. So everything's looking really, really good, and we adjusted the distortion at 1 kilohertz, as that's a typical audio frequency. We're at 98. Actually, I could speed it up a little bit, I think. No, that's 100 kilohertz. Sorry. Helps when you remember to use the tools correctly. This reads in kilohertz. 1 kilohertz would be 1.0, so we're at 970 hertz. Stretch it out a little bit more, but it takes a lot longer. So just shy of 1 kilohertz, we have a THD of 0.26. That's not too bad, especially since my target's 0.5 and my typical is below 0.3. Why I had to readjust it for 1 kilohertz and couldn't just leave it is because the AA501's frequency response tops out at 100 kilohertz. I can't adjust something at the top end and say it's good for the whole range. So 1,001 kilohertz, sorry. The AA501 will read 1 kilohertz, but it'll only give you the third harmonic because it only has a frequency response up to 300 kilohertz. So let's see what the distortion products look like on the spectrum analyzer. This HP3585 is uniquely capable of making this measurement. So what we're doing is we're taking advantage of the notch filter on the front end of the AA501, so we're notching out the fundamental. So we're actually looking at just the noise. Essentially, the way the AA501 does a distortion analysis is it goes, okay, here's my fundamental, cut the fundamental, everything else is noise. So I've got a start frequency of 900 kilohertz, I have a stop frequency of I have a start frequency of 900 hertz, a stop frequency of 300 kilohertz. So we have the functional bandwidth of the AA501, no filters installed on that. And if we take the marker, take a look at some of these peaks. So we have a 1 kilohertz signal. So that's 900 hertz. So (1.1). So 2 kilohertz would be our first harmonic. We can blow this up a little bit more. Start frequency 900 hertz. Stop frequency 10 kilohertz. Now, the FG506 is not sweeping at the moment. So we can see the diode shaper has some peaks. So it's a little below 100. So 992, 2929, 387. So these are just the levels of THD coming out of the sine wave shaper. This is still a 0.2% THD, so this isn't too bad. I mean, even at our peaks, we're still at negative 10 dBm. Now, the reason that the HP 3585 is uniquely suited to make this measurement is because it has a 1 megohm input impedance. So I have the function output of the AA501 tapped into the 1 megohm input impedance of the 3585. Not bad considering we started with a triangle wave and then shaped it into a sine wave. Okay, dropping the resolution bandwidth down to 10 hertz significantly increased the sweep time. Sweep time went to 182 seconds. But we can see that the peaks that were visible before have narrowed up significantly. So this is what's leaking through the diode shaper, taking the triangle wave to a sine wave, and is not too bad. I mean, this is considering that the shaper is just a bunch of diodes with some resistors and careful selection of the breakpoints. Nothing wrong with this at all. I could drop it down to 1 hertz bandwidth, and it'll just narrow it up and drop the noise a little bit more. However, that would take this sweep 33.5 minutes to build. So significantly longer for not much more data points. Bit more cleanup. Most units don't need this, but this one's calling for it. This field of transistors here, whenever the oscillator would stall and wouldn't behave right when I was switching the high-low and sweep, a gentle tapping on these transistors with a plastic tool would get it to fire off and go again. I know we already replaced this socket, so this socket's good. These transistors are socketed, so what I'm going to do is I'm just going to move them around in their sockets, pull them out a little bit, and reseat them, because I do have a transistor in this area that has a horribly intermittent connection, so reseating all the transistors should help, and also I'm going to inspect the sockets for corrosion or anything like that. Okay, reseating those transistors definitely made an improvement. I can now stall the oscillator at the top end. It doesn't die, and it stops at the top end like it's supposed to. And I can start up the sweep again, and the sweeping is working fine. I can also stall it at the bottom like it's supposed to, and restart it, and the sweeping is working fine. So definitely was a kind of dirty connection on one of those transistors. I do still need to clean the function buttons, because if I hit the function button, actually that's working now, it didn't before. And then we'll hit square waves. So the function button needs a little bit of cleanup, but the unit is working like it's supposed to. The difficulty at the very end of the video was actually due to a loose cue. So the unit is actually finished up and is in good shape. The troubleshooting process did not deserve an extra video, so hence why I'm shooting this little clip here. We had a loose cue up in this area that wasn't seated all the way, popped it down into the socket, and the thing then proceeded to sweep correctly for 2 days straight. So everything's all set and done on this particular unit, and it's ready to go back. Thanks for stopping by the lab, taking a look at the third video on this FG506. I think we finally got all the gremlins pulled out of it. Needed an extensive rebuild. But I do believe at this point it's ready to go back to its owner. So if you like what you see, give the video a thumbs up, hit the subscribe button, and if you would like additional content, take a look at the Patreon page and see what's out there. As always, I check all the comments in between videos. It has been an amazing experience to work on something this rare, and really appreciate the opportunity to get this on the bench. And so, one, I can bring something of this rarity back to life, and also bring it on camera for you guys to see. Take a look at the TechWiki page. Part of the process of me having this is I'm going to take a bunch of pictures, and we're going to write up a TechWiki article on it as well. So we're going to work on getting that documentation done, and a couple of things out there. As always, I'll catch everybody in the comments section between the videos. Take a look at the description section for the pinned links. I'll see everybody in the next one, and more is on the way.